Hi, I'm Akram, a PhD student at the Max Planck Institute for Software Systems. And this is joint work with my advisor at MPI Stelios and my collaborators at KU Leuven, CISPA, and Freie Universiteit Brussels. CapablePtrs is a step towards provable security for compilers to capability architectures. The compiler security criterion we prove in this work applies specifically to the scenario of compiling partial programs. Most programs we write are just parts of a bigger program, and these program parts are compiled and later linked against untrusted third-party libraries that could be buggy or even malicious. And often the program part has important security properties that must continue to hold even when it is compiled and linked against such libraries. If this implication holds, namely a secure source program part implies a secure compiled program part, then we say the compiler is secure for the particular class of security properties that our definition specifies. Our goal is to prove compiler security. Let us consider one example security property, confidentiality of secret data, in order to see what it takes to achieve compiler security. As an example, consider the following program. You don't really have to read it. It is linked against an untrusted third-party networking library. The program has a variable, secret, which is never explicitly shared with the library. And we'd like to make sure the library has no covert means to read this variable. This holds in the source, assuming that the source semantics is memory safe. However, once we compile this program to assembly, this guarantee is lost, since the library being provided in assembly can access any part of the address space, including the part allocated for the secret variable. For example, a malicious library could guess the value of the pointer to secret and leak the secret to the outside world. And a buggy library could unintentionally leak it as well through an off-by-one error when reading the I/O buffer. For example, in this buggy receive function, the off-by-one error leads to reading 1 byte of the secret, adding it to the checksum, and sending the checksum. So both of the malicious and the buggy networking libraries violate the preservation of confidentiality. And the goal of compiler security is to formally prove that if a program part is secure when linked against any library in the source, then it remains so in the target semantics. Because of the increased attack power in the target, the compiler may have to do work to isolate the compiled program part from target libraries. The compiler could enforce isolation by using techniques for process-based isolation. However, these and other coarse-grained isolation techniques will typically require changing the source program because they require that the shared memory be set up ahead of time, and they disallow incrementally passing pointers at runtime. And we do not want to place this prohibition on passing pointers. So this is our first requirement for a compiler security result. We'd like to not require a change to the source program. So for our example program, it means you'll need to isolate the secret variable by default, while at the same time allow the main function to call the untrusted receive function and to share with it the I/O buffer at runtime, not upfront, in order to avoid rewriting such a program. The second requirement we have for a compiler security theorem is a proof reuse requirement. Whole program compiler correctness is a more standard verification criterion that transfers the defined behavior of a whole source program to related behavior in the compiled version. And we'd like to reuse it without having to repeat years worth of proof effort implicitly as part of a big compiler security invariant proof. For the first requirement, we use hardware capabilities. For the second, we develop a novel simulation relation called Trickle. Note that these two requirements were not satisfied simultaneously in prior work on compiler security. Prior work either did not achieve reuse of compiler correctness, or when they did achieve reuse, the proof technique was suited only for a compiler that uses coarse-grained isolation. In CapablePtrs, we have the first compiler security proof that achieves reuse of compiler correctness and allows memory sharing through pointer passing. Our main conceptual contribution is the proof technique Trickle. We also implemented a C2C transformation that helps automate the annotations that the C programmer would need to add in order to achieve isolation in a modern capability architecture. The annotations describe a per compilation unit isolation boundary that the capability architecture and C compiler will enforce. We evaluate for 4 large open source C libraries the amount of manual code change that remains to be done to enforce the per compilation unit isolation boundary. The proportion of lines of code that changed ranged between 0.15% and 3.5% of the size of the respective library. Our observation regarding performance is that the overhead is proportional to the number of cross-compilation unit function calls. In the rest of this talk, I will give you some details about the proof of compiler security. I'll first explain what hardware capabilities are before I'll explain how Trickle achieves proof reuse. Hardware capabilities are, to a first approximation, just fat pointers implemented in the instruction set. A capability value defines an arbitrarily small memory region and permissions on this region. Capability architectures ensure two key properties. One, capabilities are enforceable. Two, every memory access instruction expects a valid capability value. There is an extension of RISC-V with hardware capabilities called Cherry. Also, ARM is experimenting with a similar extension for its architecture. By relying on such an extension, a C compiler implements pointer passing as capability passing, and we prove for a model of such a compiler that it is secure. Hardware capabilities help defend against a buggy or a malicious library. Imagine that the I/O buffer and the secret variables from the example from before are allocated to these orange and black regions of the memory, respectively. The compiler and the loader will both ensure that when the library is called, the only capability it has is the orange capability that enables it to access the I/O buffer, but not the secret. If the library is malicious and it casts an integer to a pointer, the unforgeability property will ensure the cast does not result in a valid capability and instead results in a capability with an invalid tag attached. And the subsequent dereference of such a capability will fail. More concretely, in the semantics of the Cherry RISC-V load instruction, there is a check that will raise an exception due to the lack of a valid tag. Similarly, a length violation exception will also be raised in case the well-intentioned but buggy library attempts to access the secret through an off-by-one error. Hopefully now the benefit of compiling to hardware capabilities is clear. Capabilities can be passed at runtime, just like pointers, and the lack of capability ownership implies memory isolation. Next, I'll talk about Trickle. But first, I'll define compiler security. The definition we use is standard. It is called compiler full abstraction. And it implies a guarantee similar to the setup that I showed in the beginning. If a source program part is secure, the compiled version should remain secure as well. Roughly, compiler full abstraction defines a secure program as a program whose secrets are kept confidential. The precise definition is in the paper, but I'll give you here just the intuition, which is that confidentiality is encoded using the concept of indistinguishability. A source program part is secure if no linked source library can distinguish two runs of the program with two different secrets. And similarly for a target program part when linked with target libraries. In the paper, there is a proof sketch of this theorem. I encourage you to read section 2 if you're interested. Now I'll just focus on the novel part of the proof, the trickle relation. Trickle helps structure the proof of a critical part of the compiler security theorem. This part says that the behavior of any given target attacker, the red trace at the bottom, can be simulated by some source attacker, the dashed blue trace at the top. Or in other words, the compiled target program is not more vulnerable to attacks than the source program is. To construct the witness of this existentially quantified statement, we use a technique called trace-directed back translation, which is just a meta-level function whose input is the given target trace and whose output is a source library that, when linked with the source program part, will emit a mimicking source trace. Next, we need to prove that the back translation has constructed the right witness, namely to prove that indeed the source trace is related to the given trace. For that, we'll need a cross-language simulation relation. Trickle restructures this relation by introducing a mediator execution resulting in a ternary relation, which factors the cross-language relation into two. Crucially, the invariance of the relation at the top follows immediately from the whole program compiler correctness limits. The refactoring also renders the relation at the bottom a little more convenient because it is now a same language relation in the target language. This target language relation is a turn-taking relation consisting of a weak similarity and a strong similarity. The weak similarity holds when the library is executing in order to allow us enough freedom when defining the trace-directed back translation function. Whereas the strong similarity holds when the compiled program part is executing and exploits the compositionality and determinism of the compiler to establish a lockstep simulation between these two syntactically equal program parts. The strong and weak similarities differ on how they relate memories and how they relate the control stacks. I'll focus on the memory relation. At any execution state, the allocated memory can be partitioned into three parts: private to the compiled program, private to the library, and shared between both program parts. Strong similarity keeps both the shared memory and the memory private to the program in sync, while the weak similarity only requires that the memory private to the program remains in sync while the library is executing. The trickle simulation technique relies on strengthening and weakening lemmas that apply alternately when execution switches between the program and the library. Backing up, the key benefit of our trace-indexed cross-language relation is that it introduces a mediator execution that enables us to reuse instead of reprove lemmas about whole program compiler correctness. You can find more details about Trickle in the paper, together with an example input-output of the trace-directed back translation. So in summary, we have a proof of compiler through abstraction for compiler model from C-like language to capability architecture. The proof achieves reuse of the compiler correctness lemmas, and the source language allows memory sharing through pointer passing.